Today I'm going to be working through part 2 of our exam 2 today in our Transport 2 class. In part 2 we are going to be using Python code to go through and generate some data points. Let's reconnect that already. We are going to be using generating some data points to end up solving and trying to analyze for what the exponents and the coefficients are in the Sherwood relationship that we found in the last video. And we know it's an exponential in the terms of Sherwood is equal to A times the Reynolds number to raise to the B power multiplied by the Schmidt number to the C power. And so to start that off, I went ahead and brought in all of our libraries and everything that we're going to need for that. And so going through that real quick, first one here, we have import numP as NP, which is just numerical Python, allows us to do calculations. It's a pretty basic one. Underneath that, we have from plotly.subplots. We import make underscore subplots. And so that is going to allow us to really make plots, graphs, and anything like that if we want to. Excuse me. Underneath that, we have import plotly.graph underscore objects is go. That will allow us to make a 3D plot, which is what we're going to need to do to plot and really put in the coordinates for the Sherwood, Reynolds, and the Schmidt numbers, so we can see that in a three-dimensional manner and see all three of them at once as they track against each other. And pretty much underneath that, we have import plotly.io as pio. That really just allows us to access the plotly.io templates, and really, as you can see underneath there, what we're using it for is to create the background dark, so it's just a lot easier on the eye. It's easier to look at. It's a lot prettier, really. So that was what that's for. That's the only reason that we brought that in, is just to help modify that. And then the last one that we have is the SciPy. From the SciPy optimize library, we're going to import the minimize function, which is going to help us minimize the error that we're going to have whenever we're doing the calculations for these subscore. And so to start it off, we really need to start by generating the numbers, the data that we're going to have for the Reynolds, Schmidt, and then we're going to use those values to find the Sherwood values for the two. And so really to start it off, we are going to start with the Reynolds number. We're going to set that equal to NP random, which is just going to, this is a function within the NumPy library that's going to allow us to, it's a random number generator. It's pretty much all it is. It's really easy. But we're also going to need it to be uniform, because it's a uniform distribution across the upper and lower limits that we're going to have. And so for the Reynolds relationship is good for 2,000 until 35,000. 35,000, and we are going to want to get 100 values of that. And so that's going to really just it's going to store 100 values in an array in the Reynolds RE variable, which is just going to be stand for Reynolds. And so we're going to have 100 uniformly distributed Reynolds numbers within the Reynolds array that scale from 2,000 to 35,000 in value. And then next we are going to be finding the Schmidt number. We're going to be doing the exact same thing that we did with the Reynolds number here, but the only difference is that it's over a different scaling. It's over different values of ranges that the Schmidt relationship is good for. And so this is from, instead of 2,000 to 35,000, we are going to have it from 0.6 to 2.5, because that is what it actually is for this relation. I'm just going to make this look a little prettier. And now that we have these two generated, we can use the Sherwood relationship that we have given to us in our book to really find out what, store those values that we have and to get a random uniform array for the Sherwood values based on these uniform random values and the Reynolds and the Schmidt numbers. And so pretty much the function that we were given in our book is 0.023 multiplied by the Reynolds number, and this is going to be raised to 0.83 power multiplied by the Schmidt number. Oops, I'm going to be doing that a lot, of feeling. And this is going to be raised to the 4 power. And this is just pretty much a relationship that we were already, I accidentally deleted the line. Let's type that out again. 0.023 multiplied by Reynolds raised to the 0.83 power multiplied by Schmidt raised to the 0.44 power. So yeah, that's the relationship that we're given within our book, and we're going to use that to develop our base Sherwood array for the same 100 values. And so what we're going to do before we go on and do the actual linear regression and get into our design matrix, what we want to do is we want to have some sort of account for error in our values. And so what we're going to do is that we are going to assign Sherwood values, the same exact thing, using those base 100 values that we have stored in Sherwood. We are going to take that and we are going to assign np.random.normal. And this is just a function that's in the NumPy library that will allow us to add, since it's pretty much allowing for and accounting for any sort of error to whatever we want it to be. And so for this scenario, we are going to want it to be a 10% error of the Sherwood values that we already have calculated. And just like that, we have that there, and we should shift enter, make sure that works. Trace back most recent column, there's no entropy. Oh, misspelled uniform. Whoopsies. Yep. So all's good there, and then now we have pretty much our values stored into the 3 arrays, the Reynolds, Schmidt, and the Sherwood arrays that we currently have. And so from here, what we're going to need to do is we're going to have to go in and really develop our design matrix. And so the way that we're going to do this, and I'm going to talk through it rather than write through it and do any other explanation. We're going to have our array in terms of we're going to take the natural logs of both sides first off. So we're going to have the natural log of Sherwood is equal to natural log of A multiplied by, not multiplied, plus the coefficient B multiplied by the natural log of the Reynolds plus the C value multiplied by the natural log of the Schmidt. And so what this is going to do is that we're going to allow it to pretty much change the function, change the arrays, and make it a little better. And so first thing that we're going to have to do is that we are going to have to set that array up. And it's pretty much going to be, A is going to be the first column. It's going to be a 3-column array. First one's going to be A. The first one will be the Reynolds, and then the second one will be the Schmidt. Or the third one will be the Schmidt, sorry. And so from there, we're pretty much just going to modify it so that we can help use it in Python. And so what we really need to do is that we need to set that up, and we're just going to call that design matrix, or I'm probably going to use X as a variable for it. And so this variable X is going to be equal to np column underscore stack. And then, so this is pretty much just a function that's in the NumPy Python as well, NumPy library. And this is just going to allow it to take a like it says on the screen, it just stacks a 1D array into a column, and it makes it into a 2D array, which is really nice and what we kind of wanted to do at the moment. And so, well, first number we're going to do is we're also going to import another function from the NumPy library. And all this is going to do is just going to generate the first column as a column of ones. That's really all it is, and it's going to be equal to the amount of numbers that we have in the Sherwood array. So that was going to be the first array that we're going to have within this design matrix. And next to it, we're going to need is going to be np log of the Reynolds. Whoops, I told you I was going to make that mistake again. Of the Reynolds and also of the Schmidt. Boom, boom. And so that's going to be our design matrix into Python. From there, we're going to be able to modify it in a little more. The next thing that we really need to do is we need to set up our unknown matrix. And so this unknown matrix is really just going to allow us to account for and get to modify, and because what we want to really do in the end is isolate this unknown matrix. And that will be this will be the matrix that gives us our values for the coefficient A, the exponent b, and the exponent c. And so in order to do this, we're going to have to multiply both sides by the transpose of the design matrix X. And also, we're going to have, that'll end up having to cancel out both sides. And then we'll have to multiply by the inverse of the transpose times the design matrix in order for that to cancel out. And then we'll be left with the unknown matrix is equal to the transpose of the design matrix X multiplied by the natural log of the Sherwood value multiplied by the inverse of the transpose multiplied by the design matrix, if I'm correct. And so what we need to do here is that we need to set up this value of u. And so u is its unknown that I've stated previously. And what we're going to have to do is we're going to have to do in NumPy, once again from the NumPy library, is that we're going to have to bring in linear algebra. I believe it's IMB, correct? Yeah. So yeah, it's gonna, yep, that's what we want, the multiplicative inverse. So that's going to allow us to multiply by both sides, and then we're going to that'll allow us to ultimately, in the end, isolate u. And so, excuse me. So we're going to need x as the first part of this, and then we're going to need the transpose, which is just dot t. And then to multiply by matrices, we need to use the @ symbol to multiply them. And so we're going to multiply that by the normal value, the normal matrix of x. Then we are going to multiply this whole thing by the transpose again, x dot t, and multiply that by the NumPy log of the Sherwood number. And then that really should give us what we really want to see for the values of u. And I just want to make sure, I want to print u just to make sure that this is correct. NP dot, and then because we need to raise that to the exponent as well, the first value of a, because it's not actually, it's taken to the natural log of that, and when we're doing it on, and working through it in the actual conceptually, when we're taking the natural log of a, we just have to take that back to the power of an exponent so that we see that value of a. And so a is going to be the first value in that matrix. I want to make sure that this is right. Looks like we got something wrong here. NumPy has no attribute 1 underscore the yeah, there's supposed to be an S on there. That's what that's supposed to be. And then what's your name? And that's supposed to be a capital. That's my biggest issue, is capitalizing when it's not capitalized. Alright, and that actually worked out pretty well. And so this is the values that we wanted to see, and the reason that these are, we can verify a little bit, is because this is close to 0.83, and the third one is close to 0.44, but it's also both a little bit off. And this is just because that we're accounting for that error of 10% way back up here. When we brought in Sherwood, the Sherwood relations into that array, and we're pretty much restoring the values into that array with a 0.1 error speculation. Alrighty, so now that we have verified that u is set up the way that we want it to be, because we wanted the values of a, b, and c to be stored inside of u, and pretty much by doing these matrices configuration, matrix, it's not the Penrose inverse, but it's just matrix manipulation. I'm forgetting the word. It's really just eluding me at the moment. But it's what we wanted to see, because we knew that b was going to be close to 0.83. It's 0.844 on here. And then we knew that c was going to be close to 0.44. That's 0.45 on here. So we know it's about what we want it to be. And so what we want to do now is we want to define an equation, which is going to be the sum square. I'm going to have it define sum square. And I'm just going to use a variable a. And so really what this is going to do is this is going to create an equation that is going to give us return the sum squared difference between the model and the data that we generated within the already into the Reynolds and Schmidt arrays that we have here. And so what we wanted to return here, if I could spell right, that would really help, is the sum, NumPy sum of Sherwood minus, oh, that's another capitalization error. So we want to return the numpy sum Sherwood minus the first value in that array, which is going to be a sub 0, multiplied by the Reynolds value. And this is going to be raised to the second value in this array, which is going to be what we think is going to be B. So we need it to be A of 1, which is the second value in that array, and then multiply that by this Schmidt number raised to the third value in that array. Alrighty. And then what we want to do, this is where the minimize function can come in handy. And so what minimize does is that it minimizes the scalar function of one or more variables, which it's just minimizing the error again. It's taking away that error that we put in here for right up here. It's covering it right now, but when we multiply that 0.1, it's helping to minimize that error in the objective function of it. And so we want to take the minimization of the sum square equation that we just made, and we're going to use the book values, the literature values of what they are supposed to be. And that's really because we know what they are really supposed to be at, 0.023, 0.83, and 0.44. So we know what these literature values are supposed to be equivalent to. Let's run this. Yep. And so this is about what we want it to look like down here. I've run through this before, so I know that these numbers are correct, roughly. I think I'm pretty sure. And so now that we know that we memorized in the sum square, getting it close to what these values are supposed to be, we can have all of these stored, and we really want to go through and start making our actually making the plot and storing it into the plot array. And so we can make that 3D the 3D plot make it look a lot pretty. And I forgot to state this earlier, but this is the Penrose inverse method, where we're going to end up doing that and getting, it's just another way of linear regression. This isn't the first way of linear regression right here. This is the second way we did it right here. And so just another way of doing that, and that gives us a second model right there. So first thing that we need to do to start off here is that we need to actually create our subplot. And so we need to fig is equal to make underscore subplots, and then nothing in there yet. And so this is just making the base subplot. We've done this before in exam 1. It's just making the base subplot. And what we want to do here is that we want to add a trace to this. So we want to fig.add underscore trace, and then we want it to go dot scatter 3D. And so this is just pretty much generating it in as a 3D scatter plot. So what we need to do here is that it's taking in that plot that we just made through the make subplots line, and we're adding in, making it a 3D plot. And what we need to do is that we need to add in the axes now. And so we know that x is going to be equal to the Reynolds number, y is going to be equal to the Schmidt, and z is going to be equal to the Sherwood. If I keep looking up, it's only just because I'm checking the clock. It's literally just right in front of me. I'm not trying to cheat or anything. I'm trying to be honest with you, Professor. So this scatter plot will now have the 3D plots. It'll be a three-dimensional scatter plot with the x-axis being the Reynolds, the y-axis being the Schmidt, and the z-axis being the Sherwood. We still need to add in the mode, which is equal to markers. So just create it in the form of markers when like labeling the axis. I'm pretty sure if that's the right way. And then we need marker size, which is just actually no, I'm not right. What markers is that it's actually the form of the plot that we put onto the 3D scatter plot. That's what markers are, and that's why we're doing the marker size and making it bigger. It's a little confusing. It's a lot of information. And so pretty much what that is that increases the size, make it a little easier when we actually pull off the plot and look at it. So now that we have these brought in, we need to go through and adjust and create coordinates for the Reynolds, Schmidt, and then eventually the Sherwood after we create the Reynolds. And by the way, how we're going to do this is that we are going to, first off, by going through each of the Reynolds values as that varies and keep the Schmidt values constant. And so that'll vary the Reynolds values. And then after we get those values created, we can go through and create Sherwood values that correspond with all that. And then we're going to have to go through and do that pretty much all again and do that same with the inverse, where we keep the Reynolds constant, vary the Schmidt, and then we'll still get different Sherwood values for that. But in the end, it's going to be more represent of those coordinates that's going to be put on the plot. And so we're going to be doing that by a mesh grid type of tactic where, underscore grid. Then we want the Reynolds underscore grid. Did that same thing. And so that's what we're going to do the first part. And then like how we're going to do the first line. I'm going to copy and paste it going through the second just to make it easier. Just because it's the exact same thing. We just need to inverse the first off the Schmidt grid and the Reynolds grid, as well as the regions that they are actually valid for. So like for Reynolds, it's 2,000 to 35,000, and for Schmidt, it's 0.6 to 2.5. And so, like I said earlier, once again from the NumPy, I'm going to do that. From the NumPy library, we are going to have to import a mesh grid type of function. And so what this really does, and we're going to read through this again, it returns coordinate matrices from coordinate vectors. So that's currently what we have stored inside of up here is Reynolds, Schmidt, and Sherwood are pretty much their values that we have in here, but we need to make them again because they are not in the form of a vector. And so the way that we're going to do this is that we're going to have equally spaced out numbers for the values. And so we're going to be using NumPy from the NumPy library once again as NP linspace. And then really all that does is just it generates it returns evenly spaced numbers over a specified interval. I really like this coming up because when I'm trying to think and just like go off the top of my head, I sometimes fumble my words, and that thing's beautiful. I love that. And so we're going to give that from the Schmidt range of 0.6 to 2.5, right? I just want to make sure I double check that. 2.5. And then we're going to want 25 values of these. That should be enough of what we really want to see, and that'll be all good with us. And then the next thing we need to bring in is the same thing, the NP linspace, but we need it for the values of the Reynolds that it's good for. And that will be from 2,000 to 35,000, and we want another 25 to coincide with those as well. I don't need another one, do I? Yeah, I don't know where that goes. So yeah, so that pretty much gives us our vectors, and it's going to store it into a different type of grid. And let's bring this up just so I have it right here, might as well. Come on, come up. Yeah. Nope. Come on. Come on. Yeah, so it pretty much just makes them as coordinates from the vectors that was generated. I just want to make sure I had that right. And so from here, now that we have the Sherwood grid, or the Schmidt grid and the Reynolds grid, we can go ahead and make our Sherwood grid as well. And this is going to be equal to the equation that we had, the exponential form of equation that relates Sherwood to the Reynolds and the Schmidt number, which is Sherwood is equal to the coefficient A multiplied by the Reynolds number to the B power multiplied by the Schmidt number to the C power. And so that's pretty much all it is and what we're going to be doing here. But the only thing that we need to make sure that we take into account here is that we need to take the first value and take it to the exponent, because at the very way back when we were working through and manipulating it to be able to be coded, we took the natural log of A, and we need to take that back to the exponent so that we get the actual value of A. And so this is going to be U, and this will be because we have that A value stored and A, B, and C value scored in the that needs to be capitalized already. I recognize that. In our unknown matrices, and so that's pretty much going to be the first value of there. Then we need to multiply that by. Let me close that off first off because we don't need to take anything else to the exponent. We need to multiply that by the Reynolds grid. And because we don't really want it to be these values up here, we don't want it to be the actual Reynolds value because that's just a uniform distribution from there. While these values in here is actually the lens space that's put into the mesh grid that we're going to have to make the plot. And so we want to take that to the power of the second value in our unknown matrices. And then we are going to multiply that by the Schmidt grid and take that to the power of the third value inside of our unknown matrices. Damn. I believe that's correct. And so that gives us that. I'm going to straighten this up a little bit. And then pretty much for the last thing that we need to do for creating this section of the graph is that we need to create it for, I'm going to use the variables B, C, and D. These are just going to be placeholder variables for pretty much Sherwood, Schmidt, and Reynolds numbers for when we need to graph them. And we need to put them in a zip, which I forget what this does, but that's why we have this. I just know we got to use it. So it returns a zip object whose next method returns a tuple with the ith common. Okay, so it's pretty much just going to iterate itself through all those values and then create it and store it into those coordinate points. And then we're going to use those coordinate points and plot it on the graph. That's pretty much all it's doing. And so we need to have our values of x, y, and z, or for B, C, and D actually. It's going to be our Reynolds grid. And capitalization is my issue today. Reynolds grid, Schmidt grid, because Reynolds is x, Schmidt is y. And Sherwood grid as well, because that is going to be Z. I don't need that other one. And then pretty much that is going to be our function, because it's going to be a for loop that this goes through and then stores those values in for B, C, and D that way. And so we need to go through and add the trace before we actually show this value, or show the graph. But we need to add another trace really just to go through and create the scatter, and then I want to go through and make it white lines to make it easier to look at. So we will go through and create that scatter, go scatter 3D, 3E. We're going to set x equal to B, which is the Reynolds. We're setting y equal to C, which is the Schmidt. And we are setting z equal to D, which is the Sherwood values in this situation. And so we need to create the mode as well, which is going to be lines. We want to show these lines that pretty much are going to go from the varying side up to the other side of the graph. You'll see this here in a minute. It's a lot easier to look at, really. And then we also need to create the line color, which is going to be white. Boom. And so I want to just look at the figure real quick. Make sure this runs. Beautiful. Perfect. Okay, cool. And so this is pretty much just varying the, I wish I could get this day. So it's varying the Reynolds value and keeping the Schmidt value constant along these axes, and that's pretty much where this line is showing that same graph. And what we need to do is that we need to go through and do the same thing, but we need to do it for the inverse way. And so we need to do that by flipping these, keeping the opposite constant, and varying the other one, and then also by changing these out, altering these. Oop. This will be 0.6. This will be 2.5. And I believe that's good. Oh, capitalized. Same issue, as always. And this is the money moment. Yes. And so this is what we're going to end up seeing and what we wanted to see. And this pretty much is a graphical representation of those 3D scatter plots as we verify and just go through those iterations of the 25 variables of the Schmidt and Reynolds numbers, and then it gives you the corresponding Sherwood value on the z-axis. And we can pretty much see it as the plane goes up, both on the x and y axis, that more so on the x-axis really, as the x increases, which is the Reynolds number, Sherwood increases too. As y increases, so does the same iteration, and as x and y increase, you see at the highest point is back here, where the Schmidt value is 2.5, Reynolds is 35,000, and so the Sherwood would be at the highest up here around 203. Thank you for coming, and I hope you had a good day.